Welcome to my channel. In this session I am going to explain you about mathematical definition of random process. So it is a continuation of the previous video where I have given the importance of noise in communication system and how the noise is existing in the environment. It is a natural phenomenon which is unavoidable. So this noise is random in nature, which is called as a stochastic process also, or it is also called as random process. So based on the introduction, the random process is related to noise. This random process has two properties, which is a function of time and it is random in nature. That is, it is not exactly defined or we cannot predict its output or its waveform. So generally any system will depend on the input functionality and gives the output. The actual intention of any system is to produce the output which is an exact replica of the input. But in case of communication system which is inferred with noise, that is disturbed with noise, will give an output which is an addition of noise, that is it will have input with noise. So we have to study about this feature of noise and we have to enhance how the communication system is effective in its performance. So based on it, we'll first see the definition of random process, which is defined as, so it is defined as an ensemble function of time, that is it is based on the time functionality. So it is defined as an ensemble of time functions together with the probability rule. So there is a probability rule which governs all these functionalities which is dependent on a time period, that assigns a probability to any meaningful event associated with an observation of one of the sample functions of the random process. So we can say there is lot of processes happening in and around. So based on those random processes, how it can be defined is, it is a collective functionality which is dependent on the time and it is based on any probabilistic event which is occurring along this processes. So description of this random can be explained with an example now. Consider a random experiment conducted in terms of sample space. So we are considering a sample space and we are going to take what will be the output from that sample space. So before we are going to buy a rice, we will check how the sample of rice pack is. So likewise we are going to sample some of the content of signals which is in the signaling process, that is giving us an input. So now considering this, each outcome of the experiment is noted or related to sample point and the totality of sample points corresponding to the aggregate of all possible outcomes of the experiment, which is called as sample space. So sample space contains all those points which is collectively aggregated in different points. So each of this sample point, we can say there is a sample space which is related with time. So each one will have a particular output. So each of the sample point of the sample space is a function of time simply. So this sample space or ensemble composed of functions of time is called a random or a stochastic process. So in a sample space, we can say there are lot of sample points occurring. Those sample points occurring will be based on, or it is dependent on, a functionality of time. And this contained sample points in this sample space, which is a functionality of time, is called as random process or stochastic process. So now consider the random experiment. Now I am going to show how this random space, or that is sample space, is decimated. So now consider a random experiment with a small s, denoted by small s, with the specified outcomes from the sample space which is taken in capital S. So capital S denotes the sample space, whereas the small s denotes the outcomes. So if I am taking, this is the sample space, that is the area, any area, and there are lot of sample points. Those sample points here is S1, S2, till we can go for n values. So Sn. So I am decimating it as Sn. So for that first sample S1 point, you can say the output can be, that is outcome of the first trial at sample point 1 can be shown by this diagram. That is the signals, we cannot predict those signals as the same occurrence next time. There will be a change, slight variation in the output. So for each of the sample point which is dependent on time is represented here. So the outcome of the first one is represented there, and the next one, the black one, is nothing but output of the, that is outcome of the second trial. Similarly for Sn, if I am taking for nth value, then that is the outcome of the last trial or the nth trial, we can say. So here at the sample point, you could see here it is decimated as x1 of t. So always this probability functionality, the samples are taken in terms of x of t at a particular time space s. So it is denoted as x of t. Okay. So now we are going to see how this sample trial is obtained with respect to x1 of t and the output x of t, that is at any different time locations, we can say. So this figure shows you about an ensemble of sample function, which shows ensemble means a collective of functional sample space at a particular time with respect to any time. So if we assign, so now we are going to represent, so this shaded area is a sample space. In this sample space, again we are going to represent here, this yellow color line represents the outcome. So for first sample, the output is x1 of t suffix k. So it is represented as the outcome of the first trial. So similarly you can mark it 1. So the input for that particular is, so it differs. So for each of this sample space, we can see the signals obtained or the outcomes obtained is different in nature. Hence we can say it is random in nature. We can't predict the signal will be same, ditto of the first signal whatever is obtained. So if we assign a function of time t to each of this sample point, so I am going to assign for this each of the sample point means s1, s2, s3, s till xn. So I am going to assign a sample point means that by this rule, how this can be represented. As I said, it is represented in terms of capital X. So it is x of t comma s, that is representation of it occurs at a particular time in a sample space. So it is t comma s. So what is the duration? It is occurring between minus t to plus t. So it is the total duration of the signal, that is total observation interval is 2t. How this 2t I am writing here is, so simply observe the graph value. So for drawing a graph, you will denote the central origin. With respect to origin, you will be taking right side as the infinite value and left side as minus infinite value. So here from 0 to right side it is 0 to t positive value, and for left side it is 0 to minus t. So totally if you add t plus t, it is 2t, that is the duration. So actual duration of for the signal for this particular x of t comma s is 2t, that is the total observation interval with respect to time. So t is ranging from minus t to plus t duration. So now we are going to represent for a fixed sample point. So here it can occur at any of the samples in this sample space. It can occur at any of the point. So S1, S2, S3 like Sj. So I am going to consider Xj in any of the point means I am going to fix this. So for a fixed sample point Xj, the graph for this function, so how we can represent here is with respect to Sj means how this equation can be written here is with respect to x of t comma sj. So here already we have written x of t comma s. Now instead of that s, I am going to fix the sample point as j, that is s suffix j with respect to the time. So it is called as the sample function or the realization function of the random process. So simply for any fixed sample point, if we fix that point and the functionality is called as sample function or the realization function of random process. So now we are going to represent here with respect to output, means it is nothing but output xj of t which is equivalent to x of t comma sj. So how it is represented in terms of output now is it is small xj of t. So yellow color represents the output representation, we can say. So in terms of jth value, so since jth value is taken here sj, so xj of t is equivalent to capital X of t comma capital Sj. So this is represented as equation number 2 and the previous one is represented as equation number 1. So with respect to this, if we are illustrating with respect to sample functions, so you can understand clearly this is the output yellow line and that is the input in sample space. So we can say here, predict here, output is not actually the exact value of input. So the above figure illustrates a set of sample functions with a ranging of xj, that is j ranging from 1 to n. So it is xj of t at j value which is ranging from 1, 2, 3 till nth value. So this is for third equation. Consider this as third equation. So from the above figure, again the fixed time t suffix k. So with respect to input side x of tk, what will be the observation interval with a set of numbers is given here with respect to different range of t suffix k. So here again for fixed value of tk, it is ranging for x1 till xn. So here the value of tk is same. So x1 of tk, x2 of tk till xn of tk is equal to x of our input value is x of t comma s1, x of t comma s2 till x of t comma sn. So this equation 4 gives lot of random variables, that is inside this random processes we can say random variables we have obtained. There are lot of variables which is obtained at a different sample space. So hence equation 4 says we have indexed ensembles, that is a family of random variables x of t comma s which is called as a random processes. So this is much important when you study the very new concept of machine learning nowadays. So now we will see what is the difference between random processes versus random variables. So you should understand for a random variable, the outcome of the random experiment is mapped into a number, whereas for random processes, the outcome of the random experiment is mapped into a waveform which is a function of time. So again I repeat, for a random variable, the outcome of a random experiment is mapped into a number. So random variables is based on numbers, how many numbers it has, whereas random process is nothing but where the outcome of random experiment is mapped with respect to the waveforms itself, which is a function of time. Hope this is about the random processes, how it is explained or how it is expressed in terms of mathematical equations. Hope you understood this video. In further classes, we will be studying about the continuation of this with respect to random processes with noise. What is next one topic will be about the stationary processes with central limit theorem. Thanks for watching. Hope you understood